Hey everyone, and welcome. Today, we are going to break down a concept that sounds super technical, but is absolutely key to writing smart, efficient code. We're talking about time complexity. And trust me, this isn't just some boring theory. It's the tool that separates code that just works from code that works really well, especially when you're dealing with tons of data. So, to really wrap our heads around this, let's kick things off with a little puzzle. I want you to imagine you're in a big classroom, maybe 100 students, and you've lost your favorite pen. You know for a fact someone picked it up, but you have no idea who. How would you actually find it? Just think about your strategy for a second. All right, you probably have a few ideas swirling around. Let's look at three very different ways you could tackle this. First up, what I call the brute force method. You go up to the first student and ask, hey, do you have my pen? And also, do you know which of the other 99 people has it? Then you do that for every single student. It's thorough, for sure, but you can already feel how slow and painful that would be. Okay, method 2, the simple scan. You just go to each student one by one and ask, do you have the pen? That's it. So much better, right? Then there's method 3, the smart split. You stand at the front, divide the class right down the middle, and just ask, is the pen on the left side of the room or the right side? Someone knows. You take the half they point to, maybe 50 students, and you do it again. Split that group in half. You keep repeating this, narrowing it down until you're left with just one person. Now, this isn't just about finding a lost pen. In the world of programming, these different strategies are what we call algorithms. And choosing the right one, well, it's everything. An application built using that brute force logic would be unbelievably slow. The efficiency of your algorithm can literally be the difference between a user loving your app or deleting it. So how do we actually measure this efficiency in a standard way? That is where time complexity comes into the picture. And here's the key thing you gotta remember. We're not measuring time in seconds. That's useless, because it changes depending on your computer, what else is running, all sorts of stuff. Instead, time complexity measures the number of operations, the steps, an algorithm takes as the size of its input grows. We call that input size n. So in our classroom, n is the number of students. And the language, the shorthand we use to talk about time complexity, is called Big O notation. You can think of it as a way of classifying algorithms. It specifically describes the worst-case performance. In other words, how bad can things get as n, our number of students, gets bigger and bigger. It gives us a really clear, standardized way to compare our different search strategies. All right, with that foundation laid, let's actually climb this big O ladder of efficiency. We're going to start at the very top with the absolute best case scenario and work our way down to the stuff you really want to try to avoid. At the very top of the ladder, the holy grail is O1. We call this constant time. This is the dream. Back in our classroom, this would be like you ask the first person you see and they immediately point and say, oh, Sarah over there has it. Boom, search over, one step. It doesn't matter if there are 10 students or 10 million students. It always takes the same single step. And you see this in code all the time. Think about getting the very first item in an array. The computer knows exactly where the beginning of the array is in memory. It doesn't have to look through anything. It just goes and grabs it. Whether that array has 5 items or 5 million, getting an element by its index is just one single operation. That's O of 1. So, the performance rating for constant time. It's a no-brainer. Excellent. This is the gold standard we're always aiming for. Okay, next rung down, O log n, or logarithmic time. Now this is our smart split strategy from the classroom. With every single question, we are literally cutting the problem in half. If you have 100 students, one question brings it down to 50. The next, 25, then about 12, then 6, and so on. The number of steps grows incredibly slowly compared to the number of students. This is amazingly efficient for huge amounts of data. The classic example in programming is something called a binary search. The catch is it only works on a sorted list. The code jumps to the middle element. If that's not what you're looking for, it asks, is my target bigger or smaller? Based on the answer, it completely throws away the half of the list it doesn't need, and it just repeats that process, having the search area every single time. The rating for logarithmic time is a solid good. It's super efficient, and it's the go-to method for searching through any large organized set of data. Next up, we have ON, which is linear time. This is our simple scan method. You just go to every student, one after the other. Now, in the worst case scenario, the very last person you ask is the one with the pen. So the number of steps you take is directly tied to the number of students. If you have 100 students, it could take you up to 100 steps. 1,000,000 students? 1,000,000 steps. It's a straight line. A perfect code example for this is a function to find the largest number in an unsorted array. I mean, think about it. To be 100% sure you found the biggest one, you have no choice but to look at every single element at least once. That single for loop, the one that runs through the whole array from start to finish, that is the classic signature of an O of n algorithm. So what's the verdict on linear time? We rate it as fair. It's not amazing, but a lot of the time it's just what you have to do. It's perfectly acceptable for many jobs where you just need to touch every piece of data. And now we enter the danger zone, O of n, or quadratic time. This goes right back to our terrible brute force method. You ask student number 1 about all 99 other students. Then you go to student 2 and ask them about all 99 others. For every student, you go through all the other students again. The number of operations doesn't just grow, it explodes. In code, this kind of crazy inefficiency almost always shows up as a loop inside of another loop, a nested loop. The textbook example is an old sorting algorithm called bubble sort. You see it right there. The outer loop goes through the array, and for each of those passes, the inner loop goes through the array again to do comparisons. That's n times n operations, or n squared. And our rating for quadratic time is, well, horrible. There's no other word for it. An algorithm like this becomes completely unusable really, really fast. If an input of 100 takes 10,000 steps, an input of just 1,000 would take 1,000,000 steps. You have to be so careful whenever you see this pattern emerging in your code. Okay, so seeing this all laid out in a chart really puts it into perspective, right? We've talked about the excellent O1, the good O log n, and the fair O(n). But look at what's below that. You have things we didn't even cover, like O(n log n, which is actually common in good sorting algorithms. But then you get down to O(n squared and even the terrifying O(n factorial. You can just see how the performance cliff is so steep. Our job as developers is to always try and stay as high up on this chart as we possibly can. So, we've gone through the theory, we've used the classroom analogy, but you might be thinking, okay, why does this actually matter when I'm just trying to build my app? How does this affect the real choices you make every day? Well, this slide is where it all clicks. The way you choose to store your data, what we call a data structure, is completely tied to this. If you know you're going to be doing a lot of lookups, you might use a hash table because it gives you that near-instant O of 1 search time. If you have a huge sorted list of items, a binary search tree lets you use that super fast O log n divide and conquer search. But if you just dump everything into a basic unsorted array, you're stuck doing that slow O of n linear search every single time. So here's the big takeaway. Understanding time complexity and big O notation isn't just for job interviews or computer science exams. It's a fundamental, practical tool for your toolkit. It helps you make smart decisions so you can write code that isn't just correct. It's also fast, efficient, and ready to handle growth. And that leaves us with one final, crucial question. A question we should probably ask ourselves every time we finish writing a new piece of code. It's not just, does it work? It's, your code works, but does it scale?